First of all, thanks for deciding to join us today. My name is Kacper Łukawski. I work as a senior developer advocate at Qdrant. We are building an efficient open source vector search engine, aka vector database. And today, I would like to demystify some of the misconceptions about vector search, describe different kinds of vector search, and hopefully guide you through choosing the right stack for your projects. And before we start, let me just do a small introduction. Of course, Kacper Łukawski, I work at Qdrant, and if you'd like to reach me out, here is a link to my website. You can easily find some contact details. So if you have any questions regarding vector search or how to use Qdrant efficiently, that might be the easiest way to reach me out. And obviously, I assume that we all already know how important is search in the era of large language models. For those of you who still don't understand why it is so crucial for the effectiveness of any kind of LLM-based application, let me just briefly guide you through the typical stack of any LLM-based application. AI on that diagram is not just an LLM, but basically there are like two separate models involved usually. So we all learned that the hard way that if we want to use LLMs for our private data, if you just want to bring some of your personal information to the LLM so it can use it successfully, we need to build some sort of retrieval augmented like system, RAG, that involves an additional mechanism of finding some matching documents, some relevant documents, in order to bring that to the context that we send to the LLM. And since we want natural language-like interactions with large language models, it's also pretty natural that we won't be learning how to phrase our query so the search engine can handle it. Actually, we want to use our original prompt as if it was a query to the search engine. And that's basically what is presented on the diagram here. So in RAG, we take the user prompt and pass it as a query to the retrieval system to extract some relevant information and then send it all together to the LLM so it can hopefully generate factful answer to given question. That's also a way of bringing some external knowledge to LLMs while they're used for coding. Also, MCP servers are supposed to be providing that. At least some of them are created to implement this kind of inline retrieval augmented generation for your AI coding assistant. However, building search, especially AI search, is not an easy task. Search is a complex beast, and there are various ways of how you can extract the most relevant documents given query. However, it all traces back to some sort of vectors, because the general framework of AI-based search relies on vectors. In that schema, we have documents and queries vectorized, converted into vector embeddings. And the distance between these embeddings, I mean the distance between document and query embeddings, defines the relevance. So how good match is a particular document for a particular query. And there are various flavors of vector search. I would like to cover those most typical ones and actually hopefully all the ones that currently exist. But obviously, you don't necessarily need all of them. That really depends on the data you're dealing with. So it all starts with dense embeddings. These weren't historically the first ones, but those are typically used when it comes to retrieval augmented generation, because dense embeddings are supposed to solve semantic search. And by semantic search, I mean using natural language like queries without providing a list of keywords and hoping that the model will be able to understand the real meaning of the text we send to it. If you are interested in the internals and inner workings of this kind of embeddings, there is usually like a transformer-based model, and there is a tokenizer. And tokenizer is kind of not sexy as transformers, and many people just ignore the fact that there is some tokenization happening. But basically, tokenization existed in NLP for years, and it's still there when it comes to transformer-based models. So tokenization just chunks the input text into some pieces. Those might be words, but typically we also operate on sub-word levels. So a single word might be divided into multiple tokens. There are also some models or some tokenizers that can take a few words at a time. For example, names of cities like San Francisco or New York should be treated as a whole. Surprisingly, not that many models can handle that easily. However, when we chunk the text into tokens, we can just pass that as an input to the transformer model. And surprisingly, each of the tokens gets its own input token representation, which is also a vector. And this input token representation is just a simple mapping. So each token has a single token representation as a vector. So we just have a dictionary with keys being the tokens and values being this learned input token representations. And as you can already tell, those input token representations are just not contextualized yet. They do not know anything about the neighborhood including tokens. They only incorporate the fact that a particular token was used without the whole context, because the contextualization happens inside of the transformer model. So here we have a bunch of stack layers of the transformer that just takes a sequence of the input token embeddings and processes them somehow to produce another sequence of token embeddings that are getting more and more context aware. Finally, at the very end, we receive output token embeddings, which are then pulled to create a single vector representation. This pooling might be just taking an average. So you can imagine that if you have many tokens used in the input, then you lose a lot of information just by applying that pooling. And the models are trained in a way that makes sure that the final representation, the one after pooling, represents the whole concept that was encoded in the text we provided. As a user, you do not care that much about the inner workings of the tokenizer or the embedding model, and you only want to have a single vector representation for given text. That's fine. However, I really recommend you to just be aware of the fact that choosing the right tokenizer and the right model, those are actually coupled together. You cannot easily change the tokenizer without changing the model. So that's actually something that someone else has chosen for you beforehand. Still, doing some analysis on the token level is feasible. You can see whether some of the characters you have in your data is maybe not supported. And surprisingly, if you, for example, work with sentence transformers, so these are the most popular open source models out there, you may be surprised that, for example, some of these models do not support emoji. So if you analyze social media data, you might be just struggling because tokens represented in these models do not cover these emojis. So two sentences that differs only by the usage of different emoji, like sad face and happy face, would have identical representations because those unsupported tokens are just trimmed off from the input data. And one of the interesting concepts that has been recently created was to use so-called matryoshka embeddings. The dense embeddings themselves are usually high dimensional, I mean like hundreds or thousands of embeddings. So they do not have like hundreds of thousands, but it's usually like a rather strict compression of the input data. And the most typically used models have around 1,000 up to 8,000 dimensions. However, the search performed on the vectors strongly depends on the length of these vectors, because we compare the distance using, for example, cosine distance function. And the more dimensions you have, the longer it's going to take to calculate these distances, because that's linearly dependent on the length of the vector. We just need to calculate the distance based on all the dimensions, so this is pretty clear. So the idea behind Qdrant embedding is just to train the models in a way that the first dimensions of the vectors are way more important. They carry like the most information, so we can possibly just truncate the original vectors, like 1,024 dimensional ones, and take like 1/8 of the whole vector. I mean, just keep the first dimensions of it. And that actually proves to be quite efficient if we train the model in that way. And obviously that becomes way more faster, just because you don't really need to calculate these distances with the whole vectors. And hopefully I'm gonna prove that soon. It is pretty applicable in many cases when you really care about the performance. And except for dense embeddings, we also have sparse embeddings. If you started working in search before the whole vector databases industry has started to exist, you probably are familiar with models such as TF-IDF or BM25. And the idea behind this old keyword-based methods, such as TF-IDF or BM25, might be also implemented as sparse vectors. And the idea here is that if we have an input text, each of the words used in this text gets its own dimension. So the output dimensions are way more high dimensional, the output vectors, but the majority of the dimensions are 0, because you rarely use all the words from the dictionary, because there is a dictionary, and this dictionary acts as a mapping. Each token or each word is mapped to a specific position in that output vector. So the process is rather simple. We also perform some sort of tokenization that doesn't necessarily need to be based on words. It might be also based on some smaller units, like subwords, or maybe longer ones if you just want to encode a whole phrase. And there are also some heuristics, like removing the stop words from the input data that do not provide that much value. Maybe some normalization, like lemmatization or stemming, just to get rid of the inflected suffixes. Like in that case, jumps is converted to jump, because we just want to get rid of this suffix, because that doesn't bring that much value into the meaning of the data, but brings some ambiguity, because if someone else uses continuous form of the verb, then we have a completely different word. We just want to reduce the dimensionality of the output data. And as you may see, this is just a simple mapping. I didn't really present how these values would typically look like, but because that really depends on the model and how you configure that. However, here we have a direct mapping between the terms and the outputs, contrary to the dense embedding models, which rather encode the meaning as a whole. And sparse embeddings were historically created with some algorithms like TF-IDF and BM25 that were based on the statistics of the training data. However, there are also some neural networks that can handle that, and these neural networks have a huge benefit over these simpler models, because sparse neural models do not only apply weights to the document tokens, but by term expansion, they can also find some similar concepts, some synonyms, so they can also handle different words with similar or same meaning. Like in this example, rapid is a synonym of quick, above is a synonym of over, etc. So that actually extends the scope and helps us to automatically cover the synonyms. That's something that we were dealing with in the old systems, because the synonyms mapping had to be provided by the developer, by someone who has configured the system to work. Right now, these neural sparse models can also handle that easily. And that's actually like a mix of keyword-based search and semantic search, because as you may tell, this already captures the semantics. And if someone else uses a different word, we would still be able to generate a similar representation, because those synonyms will be somehow mapped by the model. So it has some advantages over this BM25 encoding. Still, as a user, you do not care that much about how this process works, but you assume a specific format as an output. Still, it's great to understand the difference between the dense embeddings and sparse embeddings, and what are the typical scenarios of using which. Just to give you a brief overview, semantic models are supposed to be working well when you have natural language-like interactions. However, sparse vectors will be better suited for exact match, or when your users use a very specific terminology that is not well covered by the dense models. And also, if you have a very short queries, like single keyword, then the semantics of such a query is rather limited. We cannot derive it in any way. So depending on the use case, you may prefer one or the other method. One good example that I really like is when you have a very niche business that operates on some identifiers which are both known to you as a business owner, but also to your users, because those users speak the same language, like they know the terminology. For example, if you sell some sort of electronic parts or car parts, and your audience, your customers are usually experts in that domain, they won't be describing a particular part they're interested in buying as a natural language query. They would prefer to provide you with an identifier that really tells the exact part they're interested in buying. So in that case, semantic search and dense embeddings are not the best choice, and you should prefer sparse methods. Probably BM25 should be just enough. However, in many cases, you just don't know how the queries will look like. And in that case, you can build some sort of hybrid search. There are different ways of how to do that. The easiest way is to use fusion. So we have dense and sparse results that we somehow normalize because they are incompatible with each other. For example, dense embeddings may return the result from 0 to 1, so to say, and sparse results are just not limited to any specific range. In that case, if we just always choose the highest match, sparse results will be always preferred. So that's why we perform some normalization, and then we choose the set of final results based on the scores. So this is called fusion, and fusion is only based on the semantic score or some sort of score produced by the retrieval mechanism that we use. There is also re-ranking, and re-ranking might be a bit more complex. I would say fusion is just a simpler mean, but in re-ranking you can have maybe some rules, some business rules applied, or you may just incorporate some additional encoder, maybe cross encoder. So this is like a different neural network, and this different neural network is just known to work better, but it's not practically applicable if you have millions of documents, because that requires to compare to every single document you may have. So you can use some simple retrievers and then re-rank with a bigger model. And there is also another surprising approach, which is called multi-vector, that is not limited to representing your data as a single vector. And there are different ways. This is the slide that I shared before. So we have a model that applies pooling, but what if we didn't apply the pooling but just took the output embeddings of each token and use it as a representation? That actually makes sense. And there are also models that do not perform this pooling and produce this multi-vector representation based on the document tokens and query tokens. One of the family of the models is called late interaction models. So they do not produce single vector representation, but multiple vectors per each documented query. There is also Colbert, which is one of the examples of late interaction models. That's not the only one. And The way we calculate the similarity with multi-vectors is slightly different, because here we cannot just calculate the single distance, but we use maximum similarity. So we compare the distance of each of the query tokens to each of the document tokens and just choose the maximum similarity that we then sum up across all the query tokens. But you don't care that much about how you do that if you just use the right tools. We also tested last year whether that would be feasible to just use the traditional dense embedding models as if they were late interaction models, and surprisingly, that works pretty well. So if you are interested, here are some of our findings, and this is actually a pretty powerful idea, because you can use a single dense representation model like sentence transformer and create two different vector representations. One will be just a single vector representation capturing the meaning of the whole document, and another one will be just multi-vector that you can use for some more advanced re-ranking. So you use the single vector representation at the initial retrieval stage, and then you re-rank your documents based on this multi-vector representations. That proves to be quite powerful. However, multi-vector actually allows us to perform something that is super useful, and this family of models is called ColdPally. ColdPally are based on visual language models. So, for example, small VLM is just an example of such a model that supports both text and images. And these models are able to describe what's on the picture. I mean, VLMs can do that, but they can also be turned into something more useful for search, because they can represent images as a set of vectors. So now as an OCR is needed, as the VLM can encode text and image content at the same time. However, it will just produce multiple representations, and it's just way harder to just scale it properly. For example, ColdPally based on small VLM encodes each document as over 1,228 dimensional vectors. So that actually increases the amount of memory we need to have. But we also proved, this is an article, a blog post written by Sabrina, my colleague from the DevRel team at Qdrant, and this is actually an article describing how to apply binary quantization to reduce the memory requirements. I really encourage you to have a look. But you can use one of these methods depending on the problem. And if you just think about which one to choose in your specific project, then let me just guide you through the real world example. Because usually we do not work with data which is just so well structured that we can just apply this method directly. But we have lots of messy data, which might be some sort of documents like PDFs, which are multilingual, hard to parse because they contain text, images, diagrams, table of contents, and some technical content like name of the number of the page. The real meaning might be spread across multiple pages, and it's really hard to tell how to read that document, because there might be like 2 or 3 column layout used, and there are no simple ways of solving that. So I just put it to a test, and I just tested different ideas. There might be some pages that might be pretty easy to get chunked, but if you have lots of images or diagrams or tables, footnotes, you might be just struggling with doing that properly. So here are just some of the examples of the same dishwasher manual that I took for this test. Different layout, different way of describing the information. And I just tested dense versus sparse representations for the problem of retrieval on this kind of documents. And when it comes to dense embeddings, then dense embeddings are known to be able to handle different modalities, but they require us to parse the data beforehand. For example, by using some OCR tools, just to extract the diagrams, tables, and to describe them somehow to be useful for the model we selected. Even if it's just multi-modal embedding model, that still requires some chunking, which might be just hard to be done automatically. They can support multiple languages at a time, which is a huge advantage over sparse vectors, because they usually just represent different languages differently. And sparse embeddings will be better for exact match. That's something I've told you already. And if you decide not to use the simple statistic-based models like VM25, the sparse neural networks are typically also way bigger, so it's just way harder to just maintain them properly. They're just more expensive to run. So in real life, you can expect to have this kind of questions. So how can I refill dishwasher salt? That may be a typical question asked to your dishwasher manual. And in that case, it didn't really matter if I use dense or sparse methods, because the answer was identical in both cases. That was both systems were able to provide me with the right chunk. So that's okay. So that actually shows that both methods could be used, and in that case, maybe I should prefer the model which is just smaller and easier to maintain. However, if I would like to ask questions in German or Polish, then things get a little bit more complicated, because only the dense embeddings were able to provide me with the right results, because this dishwasher manual was not provided in any of these languages. However, if I would like to find the error code and the meaning of a particular error code, then dense embeddings will fail. That they just provided me with some specification, and this specification could have included this 4C term. However, it's not something I wanted to have. So yeah, sparse vectors seem to be winning in that case. But I do not know what the queries are gonna look like. So visual model might be a best idea to use for this kind of data. I'm just not showing that exact example with small VLM, but I tested it, and actually the results were identical to the sparse vectors when I asked questions regarding some exact match, and they were also working fine for the previous natural language like queries. So actually that sounds to be pretty powerful mechanism. But in many cases, running the vision-based model like small VLM may be just an issue, because that requires lots of resources also for the process of creating the embeddings. This kind of models necessarily, like, it's necessary to have a GPU to run them effectively. So it's better to just use them in multi-stage retrieval. And if you use Qdrant, you can actually build this kind of multi-stage retrieval. Like in this example, it's a bit overcomplicated, but you could use, for example, Matryoshka embeddings in multi-stage call. So you can use the smallest Matryoshka embeddings first to do like re-ranking with huge oversampling, and then they reduce the scope of search with longer and longer vectors. And on the other hand, you could combine dense and sparse vectors and fuse them with some RRF that we have built in, and finally re-rank with late interaction. And when you use Qdrant for multi-stage retrieval, you can define all the vectors to be stored in the same collection. That's actually something that you have to do if you want to use this. And you don't really need to have vector index created for the models that you would use as re-rankers. In that case, this small VLM model has the HNSW graph disabled, just because I'm never going to use it. I will never use it for the ranking. And if I just query my collection like this, I will be just prefetching results coming from sparse and dense, and then re-rank them using multi-vector representations. And that actually means that this HNSW graph does not need to be created, because it's never used as this initial retrieval, but only acts as a re-ranker on the already retrieved points. And if you have any questions, feel free to just drop me a message anytime. In the meantime, I'm just gonna have a look at the Q&A section, but I didn't see any question be asked during the session. So thanks a lot. And if you have any questions, I hope I can just answer them just after this webinar. Someone has raised a hand, but I would prefer to have a question just written to the Q&A section, so everyone can see it. And we are just on time. So thanks for joining the session, and hope that you found that interesting. And hopefully, if you are building any kind of retrieval augmented generation or just retrieval, please feel free to just reach me out in case you have any questions related to semantic or just search in general. And definitely, if you just work with Qdrant and would like to share your experience. Well, since I do not see any questions being asked, thanks for joining the session, and I wish you a great rest of the day.